Continuing, we have the sum of n equals 1 to infinity, ln of n over n squared. We want to verify that we can apply the integral test here and then actually use it. So the condition first was f being continuous, and then being positive and decreasing. So here ln of n over n squared is definitely positive for n equals 1 to infinity. The only time natural log of n is negative is when it is less than 1. So when n is less than 1. But here we're starting at n equals 1 to infinity, so this is good. N squared is also positive, so that's fine. Decreasing, well, ln of n over n squared. So n squared, it has a bigger magnitude, like it's much stronger than ln of n. So in general, n squared is bigger than ln of n. To convince you, you can always take the derivative of ln of n over n squared to show that it's decreasing. So yeah, so it is decreasing and it is continuous, because the only time it's not continuous is when the denominator is 0, which is n equals 0, and when n is less than 0. But here, n equals 1 to infinity, so we're fine. Okay, now let's apply this. We're going to borrow the same bounds, and then we have ln of n over n squared. So we're going to have to use integration by parts. We'll let u equal ln of n, dv be 1 over n squared dn, du then is 1 over n dn, v is the antiderivative, which is negative 1 over n. So we do uv, so it's negative 1 over n ln of n, minus integral v du, which is negative 1 over n squared dn. So this is just going to be the integral now, and then at the end we'll have to evaluate from 1 to infinity. The two negatives will make it positive. I have negative 1 over n ln of n minus 1 over n. And now we have to evaluate from 1 to infinity. So this is a little tricky because it's an improper integral, so I'm going to include the limit here. And usually you could just get away with it, but this one requires a little bit of work. So I'm going to plug in b for n. Then I'm going to subtract and I plug in 1. So it's negative 1 times ln of 1 minus 1. Okay. So the limit here, as b approaches infinity, of negative ln of b over b, that's technically negative infinity over infinity. So you have to use L'Hopital's rule, which essentially comes down to just finding the limit of 1 over b. I mean negative 1 over b, which that goes to 0. And this also goes to 0. So I have 0 minus ln of 1 is also 0. So I have minus 1. And so this is just 1. Okay. The integral we got is 1. It's finite. Therefore, by the integral test, the series converges. Moving on to the next problem. I have the sum from n equals 1 to infinity, 4n over 2n squared plus 1. So let's quickly look at the conditions. So continuous, positive, decreasing. This one should be obvious. I'm only working with positive numbers, so there's no subtraction, so it's always going to be positive. It is continuous because the denominator is never 0. Because if you set 2n squared plus 1 equal to 0, n squared would be negative 1/2, but yeah, that never happens for any real numbers. And it is decreasing because the denominator is a quadratic, and we know that the quadratic dominates the linear function on the top. So yeah, this is decreasing. So we can apply the integral test. So we're going to use the limits from 1 to infinity. And in order to solve this one, we have to use u substitution. So we'll let u be the denominator. And therefore, du would be 4n dn. So this just converts to du over u, which is just ln of u. And u we said was 2n squared plus 1. But we have to evaluate it from 1 to infinity. And as n approaches infinity, this thing goes to infinity. Therefore, the limit is infinite. So the integral is infinite, therefore the series diverges.